How's it going, Math 545 Introduction to Point Set Topology? My name is Tyler Battershell, and I was assigned problem number 6 for the video assignment, which is let X be a topological space and let A be a subset of X, with A a connected subspace of X. If A is a subset of B, which is a subset of A closure, then prove that B is connected. So we're going to assume that B is not connected. That means that B equals C union D is a separation of B. So by the following lemma, which we proved in class, if C and D form a separation of X, and if Y is a connected subspace of X, then Y lies entirely within C or entirely within D. And the proof is, when you assume that X equals C union D is a separation of X and Y is a subset of X as a connected subspace, then you let U equal Y intersect C and let V equal Y intersect D. So we know that U and V are open in the subspace topology since C and D are open in X, which means that U union V equals Y intersect C union Y intersect D, which, if you use the laws of intersection and unions, you get Y intersect C union D, which is just Y intersect X, which just equals Y. So then if you take U intersect V, which equals Y intersect C intersect Y intersect D, which is a subset of C intersect D, which equals the empty set. So since Y is connected, no separation of Y exists, so either U equals the empty set or V equals the empty set. Therefore, Y equals U union V equals U, or Y equals U union V equals V. So Y is contained entirely within C or contained entirely within D. So back to the problem that we have, either A is in C or A is in D, and without loss of generality, let's suppose that A is a subset of C. So that means that A closure is in C closure. So with the fact that B equals C union D, C is a subset of B, which is a subset of A closure, which means that C is a subset of A closure, which then implies that C closure is a subset of A closure, and now we have that A closure is a subset of C closure, and C closure is a subset of A closure, therefore C closure equals A closure. Going off what we have from the start, since A is a subset of B, which is a subset of A closure, and B equals C union D, with C closure equals A closure, we now have the fact that C union D is a subset of C closure. So let's take any point X and let's throw that in D. So if X is in D, then because C union D is a subset of C closure, then X must also be in D intersect C closure, which means that X is in D, which is open, and X is also in C closure, which means every open set containing X also intersects C. But since C union D is a separation of B, C intersect D is the empty set, which means that such an X cannot exist. So C closure intersect D is the empty set, which then implies that D is also the empty set. And since we now have that D is empty, this is a contradiction to the original assumption that C union D is a separation of B. Therefore, if A is a subset of B, which is a subset of A closure, then B is connected. Thank you all for watching my solution of problem number 6, and here is it all laid out on the screen for you to go through or pause or whatever you want to do to look through the solution. And I just want to say thank you for watching and have a great day.